computer presentation, so that seems so
Yeah.
so slick.
So now it seems like a regular PowerPoint presentation, like pretty old school. It's like everyone uses that like Prezi or whatever it is, or something else.
Pretty well. Well, let's go ahead and get started. So today we're going to look at transformations and then say something about paired data. But Connor's doing the first presentation on this, and so take it away.
Alright, so today I'm going to talk to you guys about transformation and the effect they have on distribution shapes and kind of how we can use these different shapes for statistical tests. Alright, so when to use transformations. Our book talks about that one of the best times to use a log transformation, which is one of the three transformations I'll discuss today a little bit. The best time to use is when the ratio of the largest to the smallest value is greater than 10. One of the main things too is when the graphical display of the original data shows a skewness of some type. Oftentimes taking, whether it's a log transformation or a square root transformation or an inverse transformation, a lot of times it'll make the data more of a normal distribution and symmetric shape. And there's some real world examples of things we think about that are on a log scale, like the Richter scale and pH scale as well. Kind of which transformation you use. Our textbook kind of gives some recommendations in general cases about when we use what transformation. In general, the best thing to do is kind of look at the distribution shape of the original data, take a transformation, see which transformation looks the most normal or most symmetric and has the least skewness and outliers. Alright, so the first data set I looked at was the Euro data set in R. The data contains a conversion rate between different European currencies. There's 11 different currencies in this data set. I listed the data set below. So when looking at the histograms of this data set, we see with the first one, the original data on the left here, very kind of, not much of a normal distribution at all, not symmetric. Most of the values are all within that first histogram bar, and then there's that kind of one small little outlier out to the right. And we see when we take the log of that graph, of that data, we get a new histogram that's, well, it's still not perfectly symmetrical and normal, it's a little more so, which makes it more convenient for doing t-tests or any other statistical tests. Alright, so the second data set I looked at was the Rivers data set in R. This data set had lengths of 141 major North American rivers, and this was measured in miles. And I listed the data set below here as well in terms of each one of these numbers was one of the lengths. So for this transformation, I looked at the inverse transformation. I looked at the log and the square root transformation. Excuse me, sorry. But the inverse was the one that created the graph with the most normal and symmetrical shape here. So I looked at that, as we see in the original one. There's a very significant skew to the right, and as we take the transformation of the data, we get a histogram that is much more normal and symmetrical. While again, not perfect, still makes it more convenient. For this third case, in the islands data set, I looked at the histograms again, but I also looked at kind of the effect that a transformation has on a t-test and some of the p-value and confidence intervals as well. So this data set has areas of land masses that exceed 10,000 square miles. So in North America is one of the ones included in that, or Iceland and a few others. It says islands, but it's not really land masses we think of islands. And this data has 48 areas, and it has a wide range of terms of thousands of square miles. So for this histogram comparison, even after the transformation, the log transformation, we still see a pretty significant skew to the right. However, it's still a large improvement for what we see originally with the original data. I would like to mention too that I think maybe part of the reason why, even with the transformation, we still get a skew to the right is we have a very significant outlier in the original data set out here. So when I took a one sample t-test, the original island data, here's the results I got. Still a pretty small p-value. That makes sense because the idea that one of the islands is 0, it's not very likely. And the confidence interval is listed below as well. So now when I took a one sample t-test of the log of the island data, we get a much higher value for t compared to the 2.5, I think it was about. Yes, 2.5-ish. And then the p-value is much, much smaller, very small. So this kind of shows how when you take the log of a data set and we do a one sample t-test on that, we can get kind of values that we're a little bit more confident about in terms of rejecting a null hypothesis. And another useful thing about the log transformation versus other transformations is you can still you can do more with it in terms of calculating a 95% confidence interval. So in order to compute the 95% confidence interval, just take the anti-logarithm, and I gave the R code I used for it right there. And as a result of this confidence interval, we get one that's smaller than the one we had for the original data. So this again kind of gives us a stronger evidence in terms of rejecting a null hypothesis. So in conclusion here, transformations, as we saw, they can affect the shape of a distribution and make it easier for data analysis, whether it's a t-test or some other, like maybe a permutation test. And transformations, as we saw, can lead to significantly different p-values and confidence intervals, and again make our conclusions or rejections a little bit stronger based on a little more evidence. And for this presentation, I looked at specifically one sample t-test, but our book goes over, it's two sample t-tests and log transformations and some of the statistical analysis tools we can use along with that. So I think it's something worth checking out. And that's it.
Great. Good job. Any questions about transformations? So yeah, that's the key points, right? So thank you very much. So on a lot of the transformations, they do change the shape, make it symmetrical. If you're doing an interval that kind of wants to have symmetry, it kind of makes a little more sense to put it on that scale and then invert it. Maybe you took square roots too, right? You can transform those back, right? So if it was something like area or volume or something like square root, cube root, might in the context really have some.
I forget what the wording was in the book, but I was reading about that and they said something about even when you take like the square root and you square, there's something that's, I forget what it said in the book, that it's not as efficient for statistical analysis as taking an anti-log is.
Oh.
I forget, I'll find it.
The log is just more powerful. It's just
Yeah.
it's more extreme, and so that might be. I mean, it's a kind of a case-by-case basis, and so sometimes the transformations. I mean, we will do something later called Box-Cox transformation. So there's ways to estimate or choose kind of an optimal transformation in a way, and that'll come up a little bit later in the book. The next student presentation will be next Wednesday, and Lily is scheduled for that. And I'll write up a sheet of notes, kind of what the topic, kind of the frame of the topic is, and then she'll put something together. But the checking for normality, there's different tests for checking for normality or graphs you might look at, and it interacts with this very strongly. But beyond the histogram, other things. So that will fit in well, I think, with the next homework and augment what's going on. So. Yes.
I just want to bring up, what it was that I read is, it said that only the log transformation, however, gives such ease in converting inferences back to the original scale measurement. It says one may estimate the difference in means of like the square root of y2 and y1,
Mm-hmm.
but the square of this difference doesn't make much sense on the original scale. So I think it's talking about, maybe this is specific to two sample.
Maybe so.
Yeah.
So, could be. So yeah, so maybe something's multiplicative, and then you take the log and it becomes additive.
Yeah.
But square roots don't quite have that same
Maybe that's it.
same functions, or something like that. Good. Close that for now. So we've mostly looked at things with one sample tests and some two sample t-tests, and then comparison, rank sum comparisons, or permutation with two tests. But of course we can do these things with paired data and one sample. Right, so the scenario in which this would occur is we would have time 1 and time 2, and we get a first measurement over here and then a second measurement, and these are the same people or the same units. It might be not time 1 or time 2, it might be group 1, group 2, but there's some matching, right? And time 1 and time 2 are typically correlated with one another. Right? If high value, positive correlation, then you have high values both times. And mostly we're thinking about positive correlations here. Right? If things are negatively correlated, that would be kind of interesting as well. But if you're thinking about positive correlation, that it's an area where size is both large in both cases, or the number of events is large in both cases, or small in both cases. So they kind of go together. Scores or medical values are high or low at both periods in time, but they're changing, right? So we typically take the difference. Yi is the difference of these two. And you could take the first minus the second if that made some sense in terms of the context, but anyway, we're just going to have some differences. And right, in other cases, we might just have just a single sample, and then we'll have our measurements y1, y2, right, up to yn. G, right? We might just have a single sample and just studying a population, and then we want to know something about that one population, right? So if we want to know something about the average of the single sample or the average difference, right? We can be interested in the mean. What is the average of y in the population? So we could be interested in mu. And if the yi's are distributed normally with some standard deviation, and the yi's are independent of one another, then the average is distributed as a normal random variable with mean mu, and the standard deviation is sigma over the square root of n, so it becomes more precise. It turns out that if you take y bar minus mu divided by the sample standard deviation, s over the square root of n, in this scenario, that this thing is distributed as a t distribution with n minus 1. If you knew sigma, I guess I could put that down here, y bar minus mu, if you could divide by sigma over the square root of n to standardize the difference between y bar and its mu, this thing would be like a standard normal in probability theory. In this one, divided by the sample standard deviation, s, so s is the sum of the yi minus y bar squared over n minus 1, and the square root of all that, right? The t distribution comes out, it's a little bit wider, and there's probability derivations that if yi's do come from that, then you do get that distribution. Right? So we're going to use, under these assumptions, we can use a t distribution for doing tests, for doing confidence intervals, about the average difference, or just the difference of this one group. Right? So with that, if we wanted to test, does the mean equal some value? This is an alternative that the mean does not equal some that value. Under the null hypothesis, that taking y bar minus the null hypothesis value over s over the square root of n would be the statistic that has that t distribution. So under the null hypothesis, this thing is distributed as a t distribution within -1 degrees of freedom, and a t looks bell-shaped like a normal, but a little bit wider, centered at 0. And so if our actual statistic is far from 0, then something unusual has happened. We've either gotten an unusual sample and the null hypothesis is true, or maybe the null hypothesis isn't true. And it's not really centered at 0, but it's really someplace else. Right. So we look at these areas up here. Say this is the area over there is 0.025, and this is, say, 0.025 area, right? These areas are called the rejection regions. Right? So this RR there is the rejection region. So we reject the null hypothesis if, right, our t statistic is greater than or equal to, or the absolute value. Because this is symmetric, we can just kind of focus on one endpoint up here. This would be the 0.975 percentile. Right? So 5%, 95% in the middle. So up to here is 0.975 based on n-1 degrees of freedom. Right? So if we're either at here or the corresponding side, we're going to reject the null hypothesis. In matched pairs, right, we very likely could have u sub 0, being 0. That there is no difference, no change, becomes a value, and so then this is just 0, so y bar over that. The changes. In some cases, though, there might be some standard increment. Right? So there might be 2% salary growth, right? 2% inflation. Right? So if you knew that the inflation went up by 2%, that measure what were academic salaries like during that year. Did they keep up with inflation? Or maybe you know that healthcare costs on average went up a certain percent. Did anything else go up with that? Did premiums go up by that amount, or did it go up more? So there might be a non-zero, even in matched pairs doing change, there might be a non-zero amount that you're interested in. But this, right, so that'd be one bit of inference, right? The other way that this you could do a 95% confidence interval for the average value, put a little y here, average difference, to emphasize what it is. And it ends up being centered at y bar, plus or minus a certain t multiple. And then the estimate of the standard error, s over the square root of n, over there. And so that gives an interval, and you're 95% confident that the actual value of u is in there. So if you're interested in 0, and you make this interval and it doesn't include 0, then you can you would reject. So if it doesn't include 0, then you would reject 0. If it includes 0, our interval happened to, well, this is a t picture of it. So if it covered 0 on this, and you standardize it, take y bar divided by this, then the t value is going to be within those bounds and not rejected, right? So that's all well and good, right? If the data are normal, right? But sometimes the data right, won't be normal. We've seen plenty of examples of that, right? If the yi's are not normal, well, if the yi's are not too terribly non-normal, not as extreme probably as the rivers or islands data, but a little bit less so. Kind of after some of the transformations, it was pretty moderate, right? So the vague statement, if the yi's are not too extremely non-normal, right, and in the number of pairs is not too small, then the hypothesis tests and confidence intervals using the using the T distribution can still be reasonably accurate. Right? But if in a smaller, 20, 30, even 40, and there's some really big outliers, then the accuracy in terms of the significance levels and the confidence interval coverage can be thrown off. Right? You have a few extreme values, even if the null hypothesis is true, could pull the intervals further away. You know, one very large value pulls the mean up, pulls the standard deviation up, and it might happen that the intervals get shifted more often than they should, and so you miss the null hypothesis more often, or you're doing a test and it happens to produce a big T statistic. Right. So this is reasonably accurate, reasonably messy, but accurate. Right. So in many cases you might still do that, right? But if you have a smaller sample size and there's outliers and skewness, right, you might want to do something to try to compare, right? Use some other procedure to say, is it still significantly different from 0 if we try to test it a slightly different way? If you're trying to make a claim based on a small data set in a high stakes situation, you probably want to be a little more convincing, right? People might ask. At least you don't want to have go forward and really press some case for something if, in fact, if you looked at the data a little more closely, it didn't quite show that. Right? So an alternative, right, would be a bootstrap. A bootstrap confidence interval for the mean, right? And you might do something with bootstrap percentiles in particular. Right? The way that this would go is if we have our data y1, y2, right up to yn, and we calculate, say, y bar as an estimate of mu. Right? Now we want to know where something's about the sampling distribution. Right? And so we can create bootstrap samples. So that bootstrap samples that look like, right, new random samples. We can't actually take more samples, but maybe we can mimic that process using our data. So one way of doing this is a bootstrap sample is we're going to sample n values, because our data set has n values, with replacement from our original data. can call those new values, say y1 star, y2 star, etc., yn star. So they're a new sample. And based on those, we can calculate a new average. And we will get very likely a different set of values, because with replacement means that we could pick some of these things multiple times. We could omit some. And so it looks like our sample, because mostly we have values that we've already seen, right? But slightly perturbed. Right? Some end up twice, 3 times, some were omitted. And so it looks a little bit different, but kind of very, very similar in a way. And if we do this process a whole bunch of times, say B, capital B times, where B might be about 1,000 or so, or 10,000, then we have many different random samples, and then we can use these different averages to describe the sampling distribution of y bar. Right? So in particular, we could either use these things to get a standard error for y bar or percentiles, and I'll write that on the next. So we have our original data, right, y1, y2 to yn, and that gave us a y bar. And then we have bootstrap samples. And out of these, we're just going to record the averages, the average at a whole bunch of different times, say capital B. And so we could look at the standard deviation of these, y bar, okay, little b stars. If y bar star b is the average for one particular sample, one particular bootstrap sample, we can take the average of all those averages, right, and square them and add them up and divide by the one less than the number over here, right? That is going to be our standard error kind of estimate of y bar. Let's work through that whole thing, right? And so instead of using s over the square root of n from our sample, this is what we're going to put in there as the estimate of that. Right? With the t procedures, we just took the sample s divided by square root of n. Here, we just have different averages, so we can look at the standard deviation of those. How typically spread out are the averages, and this can replace that.
Just to clarify, is that in this summation, are we minusing or subtracting y bar bar?
Yeah, so I just kind of use that notation to say that the average of these.
Okay. I just wanted to make sure.
Yeah. Average of bootstrap means, right, is that thing. So if you had 1,000 bootstrap samples in one vector and told R to do the standard deviation, it's just going to take the standard deviation of those 1,000 values. Right? And it should be close to this. Right? So instead of using, you might still do y bar plus or minus the t value n minus 1.975 times that standard error for the bootstrap average. You might make an interval like this. If there's skewness, this thing might end up being larger, being different, but I think it's going to be pretty close to that. So that it can be used that way. It describes the sampling distribution. But more than that, once we have all those averages, we could just look at the percentiles, right? So this bootstrap, instead of just doing that, if we had, here's the distribution of these averages, they should be pretty close to centered at y bar. They might not be exactly symmetric, right? And what we can do is find the average values here that cut off part of the tail. Right? So you cut off 2.5% from the actual values here, and then have those quantiles be the number that's in there. And if this distribution of the y, of these averages, if there were some, if the original data were skewed, then you resample, right? So if you have a situation where the original data, if the original data, the y were kind of skewed like this, right? And then you do some bootstrap samples, right? You could get the distribution of the bootstrap averages. If n is small, you might get a distribution. It'll be a little bit more symmetric than that, right? And a little bit narrower, but it still might have a little bit of a tail out there. So this one is skew, right? If n is small, y bar still has a skew distribution. And so taking an interval that is the average plus or minus some fixed about and making it symmetric might not be as desirable. Right? So instead, if you took the percentiles, you might go here, but then it might be the bootstrap percentile intervals. Interval, right, can be asymmetric. To reflect that underlying sampling distribution that is skewed. And so in small sample cases that could, work out and be desirable. But any questions? But if sample sizes are quite small, or this is very skew with some outliers, even this might seem a little bit, people might still have some concerns about it, right? So you might feel that they don't really have enough information to get a handle on this sampling distribution. That it would still have substantial skewness, and it would look a little bit funny if the intervals were vastly, really asymmetric. And people might still have some concerns, right? In a high stakes process or decision, people might want to do something else. So particularly if we have paired data, one way to look at things would be to test something else where we don't even have to, where there clearly are no assumptions. Right? So instead of testing something about the mean, right, we have these paired data, yi is the second time period minus the first. And so our data are these pairs, y1, y2, right up to yn. Instead of testing something about the mean, right, one thing we could do, right, is look at the median. What is the median difference? What is the median difference? But one null hypothesis could be that there is no difference between before and after over these time periods, in which case the median equals 0. And then the alternative could be that the median is not equal to 0 or maybe positive, right? So just as one example, right? Well, I'll start the example on the next page. Right? So in dermatology, looking at sensitivity to sunlight, mostly looking to the issue of sunburn. Say you have two ointments that you're looking at, just A and B. And you have people who are going to be exposed. In subjects, so you have 45 subjects. One way to test them would be to put sunscreen on one person, right, randomize, and one person gets A and put that on the person, right? And then do some measurement of how burned they get, right? What their level of redness is, right? You could do that with different tools for looking at redness, or ask them to evaluate pain or something like that. I mean, obviously they have to be volunteers, and so maybe they would be paid for their trouble and so on. But so volunteers in any way. Right? And so one design could be a two-sample design where one group gets A, one group gets B. Right? But you can also, with this, you could do a matched pairs design, right? You could take an individual and flip a coin, and if it's heads, put A on their left arm, right? And if it's tails, put B on their left arm, and put the other one on their other arm, right? And so they could have both on them, right? And it doesn't necessarily interact or cause that, but it also has some correlation, right? So if one person is very fair-skinned and tends to burn a lot, right? They have both on there, and they're more likely to be more red no matter what, right? Or if the amount of sun exposure or the angle which is hitting them. Now, if they only put things on A on all the right arms and B on all the left arms, and people are mostly right-handed, so that there could be kind of a bias in the sense that whatever they do, they probably do more with their dominant arm. So maybe it either gets more exposure or less exposure depending on what they're doing, right? If you're pushing a lawnmower, right, sometimes you're pushing it with one hand, and if you have a dominant arm, that one's sticking out, whatever. There could be different exposures based on that, right? So 45 subjects, each has A, B on one arm, and we can take the difference in exposure, difference in measure of redness, versus A minus B. You can flip a coin to see which arm is on there, so that would kind of balance out the left-right issue, right? And let's say in this particular study, 22 have the A arm is better. Right? There are 5 where it's about judged to be equal this redness, and then 18 where B is better. And maybe the distribution of the differences is extreme, right? So it's not a large sample size. Maybe it's clearly not symmetric. And we can be interested in testing, right? Is one better versus the other, right? So the null hypothesis, we can say, right, is the median, right, equal to 0 on the actual median of redness. And so we have 25 where A is better, so y sub I is greater than 0 here. 5 equal, y sub I, the difference is essentially 0, and this is yi is less than 0. And so we have these numbers, right? we don't want to use the y values, or maybe they're not given in an article, or maybe they're subjective, so you don't, you can kind of judge better or worse. Right? You could have people evaluating this who don't know which ointment was used on which arm, so they just should be objective to that fact. Right? So under this null hypothesis, if it's really, the median really is 0, right? What proportion of these 45 would you expect to have A being better? About half, right? So if the median is 0, right? The median in all distributions means, the central 50% point, right? So half would be above the median, half would be below. Right? No matter whether it's skew or outliers or anything like that, discrete, continuous. Right? So under this null hypothesis, right, half of y sub i's should be greater than 0, greater than or equal to 0, and 1/2 of the y sub i's should be less than or equal to 0. At 0, if it can be a tie, creates a little bit of an issue to think about and in computing, but we can look at this here. We had 22 that were greater, so we can say what's the probability that 22 out of 45, right, are greater than 0. And a p-value, if the alternative is, let's call that the probability, right, then the p-value could be reported as 2 times that probability, right? If the alternative is just that it's different. If for some reason one of these was the new one, or it was to be enhanced and better protection, more coverage, and you really thought it was going to go one way, you might do it two-sided. Right? So in R, we can calculate some of these things. So let me get that. R. Studio. Close to this old one. So we have the 22 out of 45 is, what's a little bit less than that, isn't it, right? So the 22 out of 45 is a little bit less. The distribution for, I forgot to say one thing, right? So under this, right, if we have n trials, right, and a probability of 1/2 is the probability that you're greater than 0, right, and the trials are independent of one another, then we're dealing with a binomial distribution, right? And under the null hypothesis that the median is 0, and if there's no difference, then it's 1/2 chance, right? So the number that are actually greater or the number that are less then becomes a binomial distribution. So we can calculate the probabilities that we want over here, right? 22 out of 45 are greater than 0, using a binomial. So in R, right, there's a D binomial, the density of a binomial random variable, right? And so 22 is the number we saw out of 45, and P is set at 1/2. Right? And so there's 11% chance of actually seeing 22. Right? But p-values, we say, what's the chance that we would see something that we saw, or more extreme? Right? Since 22 is less than 1/2, we are going to, zero
through 22 are those numbers. Those are all the different probabilities in scientific notation. If we round those to, say, 3 decimal places, the chance of getting none out of 45 is practically 0, right? And but here was the 22 out of 45. And if we add those up, not the rounded values, but the original ones, right, we get about 50%, right, which is not, right. What if we do it with 18? I want to just check one thing here. Right? 18 was for B, about 11%. There's a proportion test as well that does this. So let's just see. It wants, so if we put 22 in here, and the 45 trials, and a proportion being 1/2, it gives a something like that, the p-value that's basically 1, right? Basically no difference, right? It looks about equal there. So in this case, yes?
Is the sum of the D binom, is that the same as like running a P binom?
Yeah, that would be, right? So that would be a quicker way. P binom will be the probability you're at a point or less into it. So you could put 22, and then the sample size is 45, and the P is 1/2. It's about 50%, or 50%, right? So it's right near the middle, right? So probably if you had Y bars, it wouldn't be rejected. But if this was some scale where one person for some reason got extremely burnt on one type, their particular skin or genetics had an extreme reaction, then it would show up. Let's look at, if the data were different. So let's say we had 45, but A is say better in only 10 cases, and B is better, right, in 35 of them. What's the probability that 10 or fewer out of 45 occur such that A is better? And so if it's not, 22 is really quite close to the middle. And so if we do the P binom, if the number had been 10 out of 45, with a probability of 1/2, that's a very small number. Right? And if it's a two-sided, even if we double it, this was like 0.0001. If the p-value, if we double that, 2 times that value, right, very small. And so based on that, we would reject the idea, reject the null hypothesis. Median difference is not 0. And we would conclude that B is better. And recommend that one B use it. So if it ended up being more extreme, right? Maybe out of 45 differences, if the distribution was extremely skewed, many outliers, right? Some people just get fried using one of these and it doesn't provide any protection. Then doing a t-test might be a little worrisome. Right? But if you did a t-test and this one in combination, and they both gave very strong results, right? It would make things stronger. Another possibility is that the t-test could be affected by the variability, right? So if there's large variability, you might have a fairly sizable difference, but it might still end up being non-significant. Right? So if that standard deviation of the y values is large, the t-test is sensitive to that, right? And it might not be not quite significant or not overwhelming. Whereas viewed kind of this way, in terms of the medians, right? It's called non-parametric because there's no real distributional assumption. The median is always means the 50%. point, and doesn't matter the shape or any other factor. It's just always true. And so doing a test this way could give you a significant result where the t-test gets washed out because of the large standard deviation a little bit. So, but any questions about that as one alternative? There are other procedures, right? So I'll outline one more procedure. The plan on Friday is to look for things for equal variances, test of equal variances in two groups, and maybe we'll come back to another data example. So our first alternative, we did a t-test, right? You could do things with bootstrap percentiles to look at. So this is with one sample, right, or matched pairs. Or you can do the sign test for a median. The fourth one that is often done in this context is called the Wilcoxon sign rank test. So this is a matched pair procedure. Last time we had a two-sample thing, also named after Wilcoxon. That was the rank sum test. Right? So you rank the measurements from two independent groups, and then look at the sum of the ranks in the smallest one. And you would think that that should be kind of proportional to the fraction of observations that are in that group out of the total. Well, in this one, we have the y sub i's are differences. Some are negative. Some can be negative. Right, some positive. Right. And if you just look at the y bar, again, it could be sensitive to a few outlying extreme observations. Right. So this thing, we're going to drop the zeros. So if there's no difference, it doesn't figure into this calculation. That's equal. We take the absolute value of y sub I and then convert those to ranks. So if we had -2, -10, 5, 3, and 1, we're going to convert those to absolute values. 2, 10, 5, right, 3, and 1. And then we're going to rank those. Right. This would be the first one. This is the second rank, third, fourth, and fifth rank. Okay, fifth rank. Right. So on the absolute scale, rank them, how far are they from 0. Right. Then it looks at the ones where yi was greater than 0 and adds up those ranks. Add up r sub I for the y sub I is greater than 0. So in this case, the sum of the ranks is called S for sum. For these, it was ranks 4, 3, and 1. Right? And so that's what we get, plus 3, plus 1. And so that is 7, 8 is our total. Right? And then we want to decide whether that is extreme or not. If the positive values tend to be bigger away from 0, right, and the negative values are just barely negative, then the sum of the positive rank is going to be really big. If they're kind of 50-50, right, if the small values and the big values are kind of balanced out, then the sum is going to be kind of in the middle, kind of split 50-50. Right? If it's the other way and the ranks and the yi scores are generally low, right, and they make everything positive, all the big ranks on the absolute scale would be correspond to negative numbers, and just a few small values would correspond to, right, those. So you can imagine these pictures. If the y data is really kind of skewed, right, and here's 0, right. Once you take down, this will be kind of interesting, right? If I can draw this, right? It's kind of folded over. So there's these positive ones out here to 0, right? And then those this negative portion over here kind of flips around, right? And it's over there too, right? Kind of to make everything positive. But then on the rank scale, all these ranks for the negative ones are going to be kind of small, right? And the big ranks are for the positive ones. So you're going to get a big big sum of the ranks where yi is greater than 0. Right? But if it went kind of the other way, right? If you had 0 here, you had a little tail, and then more over this way, right? When you, here's the yi's, right? If you take the absolute values, right, it's going to switch the other way. So here's going to be 0. Here's the positive side. But then this negative part over here, when it flips around, it's kind of this big thing over here, right? And so the ranks of these out of all of that, I guess you get a small sum of Ri when yi is greater than 0. And if it's kind of balanced, these can be small sample sizes, so if it kind of balances out, then you'll get something kind of in the middle. Right? And so we want to try to judge, is this extreme or not? Right? So how do you judge? Whether the sum of the ranks when yi is greater than 0, right? So the sum of the absolute ring is extreme. Well, so again, under the assumption that there's, if it's centered at 0, right? And there's really no difference, well, then the difference, the yi xi2 minus xi1, is that difference is just created by random, right? You get one measurement at the first, one measurement at the second. You could just flip them, right? And another sample could be created by randomly picking our new measurement is either yi or negative yi with probability 1/2 for each I. And so that goes for I going from 1 up to whatever n, right? So if we create another sample and we do this, say, 1,000 times, right, we'll get a distribution. Centered around 0 of this sum. The sum of the ranks. So we randomly do this for the new sample, calculate the absolute values,
And then add up the ranks, the sum of the ranks for the ones that are now positive. And if it was kind of balanced before, then we'll be pretty much in the middle. And our random permutations will have our values kind of in here. But we can kind of reject, this will be our rejection region. In this case, right, we're going to reject the null hypothesis, reject zero difference, if our value of S is extreme relative to this. So this gives us kind of a fourth way of looking at things, right? So particularly if you have small data sets, particularly if they're skewed with outliers, it wouldn't be, and it's really kind of the critical thing. In a report, you might only present one of these, right? But it's good to know that you check them or are ready to defend a conclusion. And sometimes, just within a sentence, you can have the t-test p-value, and you can have the Wilcoxon signed rank p-value. And if they're both quite small or consistent or very large, consistent with each other, it's very efficient in terms of reporting, and you've kind of covered the basis in terms of not doing something that is a little suspicious. People really wonder about the assumption. So we'll come back on Friday, have more of a data example, and talk about, return to the two sample thing with variance. Thanks again, Connor, for the first presentation. This is from Monday. Oh, yes, homework. Thank you. Forgot to answer that. Thank you very much.
Can I see you probably in there, Abby? Bye.
I did that on Simon's exams in linear, where I finished the front side, and I'd be sitting there, I was like, maybe I didn't do all of it. Maybe there was more.